Good afternoon, everyone. Thank you for coming. My name is Ossian O'Reilly. I'm a HPC application optimization engineer. And it's my pleasure to talk about a topic that is near and dear to my heart, and that is stencil computation on the GPU. This is joint work together with SM Morsi at AMD. Unfortunately, he couldn't join us today, but he sends his regards. And in this presentation, I'll take you through a couple of optimization strategies that you can apply for seismic stencil computation, go over some old and gold, but also hope to bring some new ideas to the table. Is that? Okay. So some background. RTM and FWI, as we all know, are computationally intensive techniques that enable high-fidelity seismic imaging. And for this purpose, GPUs are prevalent. And a key component that is performance critical is often the wave propagator that's responsible for simulating the seismic wave fields as it advances in time. And one of the most common discretization techniques is the high-order finite difference method. And the key component to achieving high throughput for this type of application is to pay attention to how that stencil computation plays out on the GPU. And for this purpose, what we're going to do is we're going to start simple. We're going to take your most sort of naive implementation you can find. But I think this is a great starting point. You code something, you want to get it up and running fast and focus on correctness, making sure all your tests are working. Everything looks beautiful. You know, maybe you can sneak home before rush hour traffic hits. And then come back fresh next day and start the fun work, which is to start optimizing and going through a couple of optimization cycles. So what we'll do is we'll go from that easy to implement and add a few optimizations, and then we get to 10x. And of course, that 10x comes from we're starting kind of at a poor implementation from a performance perspective, but correctness comes first. And so the hardware I'll be using for demonstrating these optimizations is the AMD Instinct MI300 accelerator, which is an APU, so it combines both CPUs and GPUs. They share the same physical memory, which is pretty cool because it eliminates hosted device data transfers. And if we take a closer look at this accelerator, what you find, the main computational elements are the accelerator complex dice that contains your compute units. Inside each compute unit, that is where you have execution units responsible for doing FP, int, math, as well as also contains lower levels of the memory hierarchy, like your L1 cache. And these accelerator dice, they are packed in pairs on top of what's known as I/O dice, which contains system-level infrastructure, infinity fabric links. And also from a programmer perspective, when it comes to the MI300A, you can program this device, even though it has these individual XCDs, as one big GPU, or you can split it up into 3 partitions. It also has last level cache, which is the infinity cache, which is pretty large, 256 megabytes in size, which help reduce off-chip memory requests. And it has 8 stacks of physical HBM memory and with a peak theoretical bandwidth of 5.3 terabytes per second. So let's get started and move on to stencil computation. And in particular, we're looking at acoustic TTI. When you solve that in second-order form, one of the things that you find is that you get 2 types of stencil patterns that emerge. You have the star-shaped stencils coming from your divergence terms, but then you have also these rectangular stencil patterns that comes from your mixed derivatives. And you can see, just looking from the number of elements you have, you know, one there which has the radius and the diameter linear in that, the other one scales with the square of it. So you're going to have to find a lot more compute or memory requests coming from the mixed derivative pattern. So the key to achieving good efficiency for acoustic TTI is really focusing on how you do these type of mixed derivatives. And to evaluate performance, we need a benchmark. So what I put together here is the formulation coming from Fletcher's 2009 paper, which contains 9 3D arrays. Instead of solving a real problem, I just chosen to randomly initialize the wave field, keeping things a bit more simpler, but at the same time avoiding any hardware compression effects that otherwise will improve your performance results. I didn't want to include that in the measurements. And then I use an average of 100 iterations, and it's the interior stencil only, so no boundaries. I know in practical applications, of course, you want to have a PML or something to dampen up outgoing waves. Stencil radius is fixed at 4, and then throughput is the performance metric that we'll be looking at, which is just a computational volume divided by the average kernel execution time. And also one last point, you can estimate an upper bound on the performance you can get on your device based on the streaming performance. So you know your device achievable bandwidth and the number of arrays you're streaming, you get that upper bound. And I'm going to take you to about half of that today for the optimizations we'll do. And so one of the things you can do is think about from the start is that you've got to expose parallelism, which comes from decomposing your computational domain into tiles. And there are various ways in which you can do it. And I'm distinguishing between 2 cases, overlapping version and a non-overlapping one. And in the non-overlapping one, you have your sort of thread blocks, which is really mapping to your tile. They are right next to each other. And they have to load the halo region of data in order to perform the stencil computation defined by the radius R, whereas in the overlap tiling, you can see the thread blocks are overlapping each other by that stencil radius. And I like to focus really on the overlapping tiling today. And the reason is because it can simplify your implementations. Because often what we need to do for performance is to use shared memory, which is your user programmable cache, and which requires writing instructions for loading data into the halo regions. But with the overlapping tiling, you avoid that. It comes for free. You don't have to write that. So, but the question is, can we get it to work well and achieve good performance with it? So if you start out with these basic global memory implementations, simple to write, to find the non-overlapping tiling versus the overlap tiling versions, you see, yeah, there's definitely a benefit of using the non-overlapped version for various reasons. And also, here in the beginning, throughput is very low, so we have some optimization work ahead of us. Regardless, I'm going to be comparing our global non-overlapping as our baseline, and then we're going to take the overlapping and start optimizing it. First, let's understand the performance bottleneck a bit. So what is it? Well, if you have a rectangular pattern like this, you're really generating a lot of stencil accesses that are generating memory requests. Each such point results in a global memory request, and every memory request puts high pressure on your memory hierarchy. So that being your caches, your L1, L2, your last level cache all the way up to HBM. And what you can notice is that when you look at the bandwidth for these various levels, is that the bandwidth, right, it drops off. The closer you are to your vector registers, the higher the bandwidth. On the other hand, latency, right, it goes up the further out you go. And so the kind of optimization strategy is, you know, to divert the pressure away from the higher levels of the memory hierarchy, push it down to the registers. And also here we haven't even tapped into that shared memory, which on AMD is called your local data share. So our optimization strategy really is to tap into these resources first and foremost, bring out the performance. And one really common optimization technique you can use is this so-called sliding thread block technique, which moves your global memory requests. You reduce them instead by using vector registers where you store a computational volume of the wave field, just enough to compute the stencil in that vertical C direction. So you can get a slice, and then you sort of can load in the next slice, compute the next element, and so on. You can proceed. Really well-known, powerful, and useful technique. So we use that. And now let's look at how do we do the mixed derivative, right? So if you just think about it naively, right, you have the current approach where we have a big rectangular stencil, we have loads and stores and compute, they all scale with the number of elements there, which is d squared, where d is the diameter. But if you look at it, you can decompose the derivative. You can apply it first to one variable, and you can store an intermediate, and then you can apply the other derivative to that intermediate result, which is such called a two-pass approach. It would be going from your, one example is you have here solving the wave equation in second-order form, and you can also solve it in first-order form, right? And then you don't have any of these mixed derivatives. You have first derivatives instead. And but if you do it that way, you know, you're going to have a lot of memory requests for global memory. So we try to bring that two-pass approach down to the lower levels. We do it in shared memory and in registers instead. And here's a little idea how it works, right? So you have your vertical slice, you store that in your LDS, you sync, wait for the data to be available for all your threads, and then you can compute it in LDS to get the next one, and boom, you have it in the result eventually. And this is where that overlapping techniques comes in, which is nice because now you don't have to load any of that data in the halo regions for having to store both the wave field, it sort of comes for free, there's no extra logic, and same in that step. You also don't have to have any extra logic for having the derivative inside the halos. And so with those two optimizations, we gain nearly a 7x speed up. But we want more, so what do we do next? Well, we can take a look at the tile size itself. And in particular, if we look at that halo region, what are we doing there? We're just loading data. We're not computing, we're not storing anything there. So ideally, we want to minimize that fraction. So the only way I could think of how you minimize this is to increase the thread block size itself, or the tile size, I should say. But the thing is, the thread block size has an upper bound on 1,024 threads. So one way you can get around that is by letting each thread process more than one element per thread. And a good strategy is to use vector instructions. And the reason for using vector instructions is that it reduces your number of global memory requests you have, because a vector instruction, you can pack more data into it. So instead of doing like 32-bit, you can go all the way up to 128 by using float 4 instructions. Now, the trade-off is you start using more vector registers, you start using more LDS. So you might not get a perfect scaling of a factor 4 here. So, but the optimized thread block size is now a factor 2 bigger than compared to what we had before. The aspect ratio is a bit off in these drawings. And with the vector optimization, we gain another 1.3x speed up. So what can we do next? Well, here's where I think it's an interesting idea, is that currently when it comes to these vector operations, and it's tied to data streaming, that for efficiency, a good rule of thumb is you want a multiple of 64 in your x direction for your thread block size. And what you realize though is that naturally then, if you also have a vector, that's 4 elements in that, you get a really wide thread block. And that can be a problem, right? You come to a boundary and some of that thread block sticks out, and you lose the efficiency. And also, you need at least like 9 threads in the y direction to capture both the stencil radius as well as the compute So to get around these issues, what you can do is you can change the underlying data layout itself. So we move away from this standard approach where all the elements are contiguous in the x direction, and instead we let some of the elements be contiguous in the y direction, but just for that little vector length. And so in that way, we now have a very wide thread block size, but our tile size stayed the same. So thereby we can tap into the benefits of having good streaming efficiency for such a thread block configuration while circumventing the other issues. And so with apt optimization, you can gain another 1.15x, and now we got nearly a 10x speed up. And just to show the performance across different grid sizes here, you can see that it achieves fairly consistent throughput as we tested it for problems going up from 300 up to 1100 here. And so just some conclusions here. I like the overlapping approach because it reduces your coding complexity, because you don't have to worry about that halo logic. And then your bread and butter techniques with doing mixed derivative computation using the sliding thread block together with 2-pass in LLDS or registers, and add on vector instructions to increase your tile size and achieve higher streaming efficiency, and also then reorganize the data layout to suit that more better. And so that's it. Thank you for your attention.
Thank you very much. That leaves us with plenty of time for questions.
So, hello?
Hi.
If I understand correctly, that's an 8th order stencil that you're using there.
Yes.
And you're caching a lot of data in LDS.
Yes.
What percentage of your LDS have you used for your current block
so
size?
the LDS size is 64 kilobytes that you have. And in this case, I need to remember the number of arrays that you need to hold. You need to hold at least 2 for pseudo-acoustic because you have 2 variables. But I think you pretty much used up all of it. You're running 1 thread block per CU. So you're running in a low occupancy setting because you traded your occupancy for using more registers in LDS instead.
Yeah, which is great for 8th order, but then I guess if you expand that spatial order a little bit, you'll probably have to shrink your block size down to match.
Yes, I'll imagine so. Yeah.
Thanks.
So I just tested it here for 8th order. So we'll see how it goes if we go to higher order.
When you're loading the LDS, is that something that can be done asynchronously, or is it just something that happens as part of the normal loads?
It requires synchronization on AMD GPUs that you have to synchronize. Now, you can do other things as you're loading into the LDS. It's just that we don't have any async LDS instructions, right? So once your waves reaches that barrier, they need to wait at that barrier, and they cannot proceed doing anything else. But you can first put your LDS load instructions, right? And then you can do something else. It's just once they hit the barrier, that's when they have to stop.
Well, maybe I can ask a question. You mentioned the stream-derived high watermark for the throughput.
Yeah.
And I thought you mentioned that you're going to take us to about half that.
Yes.
Did I miss where you actually talked about the
so yeah, it requires some inference, right? So here you see we get to about 43 or something like that.
Yeah,
so yeah, and the bound I put was at 86.
Yeah. And that is assuming how many loads from global memory per input point?
The ideal amount, yes, the number of arrays that you have.
Okay.
So you have 9 arrays, but they need to store, so that's 11, and then just treat them as the 3D arrays, basically. So Not counting for any overlap in the halo radius, anything, just the ideal amount. So,
Okay.
yeah.
Well, if there are no more, oh, shucks, getting a bit of a workout here.
I just want to ask you a question. If do we expect the same speed improvement if we push the order from 8th order to 16th order, and we apply the same vectorization technique or say the pipeline technique in your optimization?
So now I can only speculate, right? Because I haven't actually done it for higher orders than what I had there at this point. I'm expecting that you see a performance drop because you're going to start having to use more resources, right, for those halos as the halos start increasing. That's sort of the challenge you have, right? So what that performance drop is, ask me in a few months.
Will do. Okay, thanks again.